Welcome back to Differential Calculus. In this video, I want to pull together the things we've talked about in the last couple of videos and talk about evaluating integrals. Let me get my head out of the way, and let's start off with a review of the vocabulary. We've talked about three related but distinct concepts, three related but distinct processes that we can do related to integration. The antiderivative takes a function little f and generates a new function capital F of x such that capital F prime of x is equal to little f of x. The indefinite integral we denote using the integral sign little f of x dx, and this is the family of all antiderivatives. Capital F of x plus an arbitrary constant of integration. The definite integral, we use the same symbol, but we put limits of integration, a and b, and we can evaluate that using the fundamental theorem of calculus. We can also think about the definite integral as describing the area under the curve. So the first thing to pay attention to is which of these the problem is talking about in any problem-solving situation. Conveniently, the antiderivative is important and is the first step of the process for either the indefinite integral or the definite integral, but it is never something that you're going to be asked for on its own. The indefinite integral and the definite integral are the places that you're going to be asked to come up with one of these. The antiderivative is a step in that process. When you take the indefinite integral, the result that you get is a function, or technically speaking, because there's an arbitrary constant, it is a family of infinitely many different functions that are related to each other. When you evaluate a definite integral, the result is a number. The indefinite integral has no limits of integration. The definite integral has limits of integration. It uses the same symbol. Those limits play a key role. So the first thing to do when you have an expression in front of you that is written using an integral symbol, you look at it and ask yourself, is this a definite integral or an indefinite integral, which you can tell immediately by asking, are there limits of integration? If there are limits of integration, you are going to use the fundamental theorem of calculus and you are going to get a numerical value. If there are no limits of integration, you are going to find an antiderivative, you are going to add a constant of integration, and you are going to get a function as the result. Definite integrals are immediately applicable. Any application problem that is going to involve you writing an integral in order to solve is going to involve writing a definite integral. Indefinite integrals are going to be parts of bigger processes. I've mentioned differential equations a couple of times. That's the key goal. That's what calculus is really driving towards. In differential equations, you use indefinite integrals as part of the process, and then you use other facts about the situation, which we call initial conditions or boundary conditions, to figure out what the constant of integration has to be to satisfy your particular needs. both are definitely valuable for different reasons. And really the point of integration in this course is to get you comfortable with the vocabulary and the fact that both of these things exist. Application and building up from there is something that we'll spend a lot more time with in the future. So let's just take a look at a couple of examples. Sorry, I'm starting to write two different examples on the screen at the same time. The integral from 1 to 3 of x squared minus 9x to the fifth dx. This is a definite integral. Again, we know that because there are limits of integration printed in the integral symbol. So, we need to find any one antiderivative here. Using the integration rules, the power rule and linearity, an antiderivative for x squared is 1/3 x cubed. An antiderivative for x to the fifth is 1/6 x to the sixth. Then we multiply by 9. I'm going to go ahead and take the step of reducing 9 over 6 to call it 3 over 2. Technically, I don't need to do that, but it makes me happy, so why not? At this point, you can always double check your work by actually evaluating the derivative of the thing that's inside the brackets. The derivative of 1/3 x cubed is 1/3 times 3, which is 1, times x squared. The derivative of 3/2 x to the sixth is 3/2 times 6, which is 9, times x to the fifth. And because this is a definite integral, we need to know any one antiderivative. We don't need the family of all of the antiderivatives. I don't need a plus c here, just putting the value of one function down. And whichever one is convenient, right? I could have just as easily called this 1/3 x cubed minus 3/2 x to the sixth plus 7, and it would give me the exact same answer. But that extra plus 7 is just more work that I don't need to do. So I can leave it off, and I'll be equally happy. All right. From here, evaluate at the limits of integration. So we will have 1/3 times 3 cubed minus 3/2 times 3 to the sixth. Then we will have 1/3 times 1 cubed minus 3/2 times 1 to the sixth power. 3 cubed is 27. 27 divided by 3 is 9. 3 to the sixth power, I don't know offhand, let me grab my calculator, is 729 times another 3 is going to be 2,187, which is an odd number, over 2. I'm just going to really hope that I have some extra over 2 that will make this work out nicely. If not, my answer will be a fraction. And of course, it's going to be a fraction anyway because I have an extra over 3 hanging out over here that I can't do anything with. You can approach from here in any way that you would like. You can even just have a calculator handle the rest of it if your calculator can handle fractions. As a general rule, I'm going to look for results at this point in exact values, which means fractions, not decimals. But things here actually are pretty straightforward. just don't forget to distribute that subtraction. I cannot tell you how many times I've seen a student get lazy and subtract instead of adding that last bit. And when I say I've seen a student, I mean I've seen myself when I was a student doing that more times than I can count. But now if I combine these, negative 2,187 plus 3 is negative 2,184, which is nice because if I divide by 2, I get a whole number answer. And then I can do 9 minus that to get negative 1,083. And unfortunately, nothing else I can do here, so just multiply by 3 to get common denominators, then subtract. I get 3,248 over 3 as the final answer. I'm sure I've talked about it in this course before. Fractional values like this are what I call answers only a mathematician could love. It is the exact value. There is no rounding. There's nothing weird that has happened from here. And there are some purposes where that is useful. I don't know of many, I'll be perfectly honest, but every now and then it comes up and it's useful and it makes things work out. So this being a math class, these are the sorts of things that we have to do. This is an acceptable answer. Punching that into a calculator and getting a decimal approximation is not an acceptable answer for this course. All right. And it helps if I hit the right button. So, paying attention, making sure that you recognize whether you have an indefinite integral or a definite integral, making sure that when you have a definite integral, you get a numerical answer, making sure that when you have an indefinite integral, you get a function as an answer, and I would like you to look at the integral from 0 to 7 of 1/6 x squared minus 1/14 x dx. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.